Hi, my name's Dean. It's a short presentation on rigid body kinematics. It's for the Engineering Mechanics 2 assignment. So yeah, this is a topic we studied last year. So let's get into it. So what is a rigid body? So throughout previous topics of kinematics last year, we studied motion about a point or a particle in space. So rotation wasn't really taken into account. That's what rigid bodies is all about. So rotation of some kind of object which is more complex and shape and size are taken into account. So motion of these bodies take into account not only rectilinearly but curvilinear and rotation. So why do we need these rigid bodies? Rigid bodies are pretty fundamental in most mechanical systems. So examples of them include camshafts, gears, wheels, linkages. Pretty much anything that rotates can be modelled as a rigid body to help design and analyse these kind of systems. As you can see here, we've got a lot of rigid bodies set up in a motorcycle swing arm. So that's just one application, which is a fundamental part of the invention of the motorcycle. So the equations of motion used. So when we're analysing rigid body kinematics, we pretty much use the same equations which we used when we were doing particle kinematics. So we've got velocity and acceleration in a straight line, then we've got rotational velocity or tangential velocity, then we've got normal and tangential acceleration. So pretty much we use all of these to find out different velocities and accelerations in the kinematic problems. And we only really consider this on a 2D plane in Engineering Mechanics 1. So when we're working out body motion problems, easiest way to find out the different velocities and accelerations of the body is to use relative motion equations. So that pretty much represents one end with respect to the other in terms of either velocity or acceleration. So if we're looking at the motion of a rigid body as a stationary observer, you can see that the motion has both a translational part and a rotational part. This is evident in the actual equation of the relative velocity equation. So if we have the velocity of A, like in this picture here, that's equal to the velocity of B in a straight line, so it's translational motion, plus the velocity of A with respect to B, which is its rotational motion of A with respect to B if we fix B. The velocity of A with respect to B always points in a tangential path of if we fix B and make A swing around it. So in that case, we can use the tangential velocity equation where it's equal to its angular velocity times the actual length of the rigid link. And when finding these velocities, the easiest way pretty much to do this is to construct a velocity vector diagram. So you'll probably be given some velocities and angles as such, and you can then go ahead and construct the polygon, the vector polygon, then work out any unknowns using trigonometry. So examples can also be found as a similar technique to that of the relative velocity method. As the equation is pretty much the same, so you've got acceleration of A, which is equal to acceleration of B, plus the acceleration of A with respect to B. So it's got that translational part and the rotational part. However, because we've got a rotational acceleration, we have to take into account that there's a normal acceleration, so it's like a centrifugal acceleration plus a tangential acceleration. Like the velocity equation, we can use the constructive diagram, find out any unknowns, and then go from there. So the normal acceleration is equal to the length of the link times the angular velocity squared, so just like the centrifugal motion equation, and then the tangential is the angular acceleration times its link. So we'll finish by just doing an example from the textbook. So what we've got like a rigid body link that's constrained on wheels in kind of like channels. So it says here that end A of the link has a downward velocity of 2 meters per second during an interval of its motion. For the position where angle theta is 30 degrees, determine the angular velocity of AB and the velocity of the midpoint. So we'll pretty much just write down the equation. V of B is equal to V of A plus V of B with respect to A. And as you can see in the diagram that I've drawn down the bottom, you can see that the velocity of b with respect to a points perpendicular out from the link. So that's just if you fix a and make b swing around, the velocity will be on a tangent path. Then from there we can construct our vector diagram. So we've got VA acting downwards because that's going to go down inside that channel at 2 meters per second. And then we know the direction of V with B with respect to A. That's going to point 30 degrees up from the horizontal. And then we also know B goes across, so if we put into that equation, follow the design convention, and then go from there, we can use trigonometry pretty much to find out the unknowns. So using the basic trig, we've got the V of B with respect to A is 2.309 meters per second. Then we can use the relationship of the angular velocity and the length of the rigid link dividing by the length of the rigid link to find the angular velocity as 11.55 radians per second. And that was one part of the question it asked. So then to find the velocity of the centre, we can use the fact that the velocity of g with respect to a pointing in the same as the velocity of b with respect to a, but just halfway down. So that's obviously going to be half the velocity of v of b with respect to a. Then using the relative motion relationship v of g equals v of a plus v of g with respect to a, that'll give us basically the direction of v of g. Then using the cosine rule and the other parts, like we've got the v of a of 2 meters per second, we can find out v of g, which is 1.155 meters per second. And that concludes the video, so yeah, thanks for watching.